period. Just the grades, probably not the whole test. But we're going to start a new chapter on the properties of these organic compounds you've been learning how to name. That's what we did last chapter. I told you it was like a, well, think of it like a language. You know, last chapter was about the vocabulary. Right? You had to learn the vocab words, like you would have to learn in any language. But then, once you learn what the words mean in French or Spanish or whatever, you've then got to put them together in the sentences, and that's what we're going to do in this chapter. You're also going to want to learn, I'm going to do it a little bit off of the language analogy. I'm also going to teach you about the properties of each of these different kinds of compounds. Now, you might think, well, how many different kinds are there? We only learned about really alkanes, alkenes, alkynes, all right? And that's what we're going to start with the first couple of days. But there is a lot more. And we're going to talk about each of those alcohols. And when we get to that one next week, we'll be finishing up that lab on fermentation. Starting with fermentation, it's going to end with something else. And a lot of other things we're going to talk about. Esters and carboxylic acids and all kinds of stuff. So we'll talk about the properties and how they react. So now we're writing sentences. We didn't just learn that we're going to put the words together to write sentences. That's what we're going to be doing in this unit. Okay. Oh, never did my... Okay. All right, and we're going to start with the one that you're probably most familiar with, alkanes. Let me give you the papers for that. Alkanes are what we wrote mostly in last chapter. They're the guys that are just, you know, a hydrogen and carbon together. That's it. Although I am going to be able to put stuff on them, and that will be part of the reactions. And I'm going to be able to do stuff with those alkanes. That's what the reactions come into play. But let's first start talking about the properties of the alkanes. Okay? Properties of the alkanes. There is some, I don't think I think I kind of gave you the wrong impression saying that, you know, up until Thanksgiving, we're going to be doing organic, and there's not, you know, really any organic on the AP. There is organic on the AP. There's just not a whole lot of it. But you probably already noticed in the AP thing you did yesterday, there were some things about hydrogen and carbon on there. There were some questions, not many, but there were a few. Some of the things you might need to know about, or would be about alkanes, that would be a very common one. And some of these substitution groups that I'm going to talk about, these other groups like alcohols, when you put other things on. So there is some of that on there. It's just not as much as the other stuff. All right, let's talk about some of the properties of alkanes. First of all, they're chemically inert. What does that mean? Well, they're like you in that way. What does inert mean?
Not moving.
Yeah, not moving, not doing anything, right, inert. They are not very reactive. Kind of like you guys. Just kind of sit there. Inert. Of course, some of you are also nerds. Anyway. All right, so they don't react very easily. This is kind of funny because when I get to the reactions in a minute, the very first reaction I'm going to do, I have a little demo for you, although I'm going to do the demo a little out of order because of people on the... I can't turn the camera around and show it. It takes a while to get it to work. I'm going to do that back there. The very first reaction I'm going to show you is the most important reaction probably for our society in civilization. Okay, what do we do with alkanes that keeps us alive and warm in the winter and transports us from place to place? What do we do with alkanes? We burn them, yeah. That's the number one reaction. It's a funny thing that, for the most part, alkanes don't react a whole heck of a lot. They don't have a lot of different kind of reactions. Alkenes have way more, and a lot of the other ones I'm going to talk about have way more reactions than alkanes do. But the one thing that they do happens to be really important, and that is combustion, burning, oxidation. Okay? We're going to talk, that'll be our first one we're going to get to in a minute. But let's keep up with the properties here. These guys are generally going to be nonpolar, insoluble compounds. Why? Because the carbon-carbon bond is clearly nonpolar. Why does the carbon-carbon bond have to be nonpolar? What's the difference in polarity between carbon and carbon? Zero. And the carbon-hydrogen bond, if you look it up, is only about 0.36 for an electronegativity difference. So that, too, is nonpolar. It's less than 0.4. So both of those bonds, and if I only have an alkane with nothing else on him, I don't have any O's on him, I don't have any chlorines or fluorines or bromines on him, then I know that the alkane is going to be nonpolar. It's not going to dissolve in water. All right? Because remember the one rule about solubility. like dissolves like. Remember that from Chem 1. Like dissolves like means polar things dissolve, charged things dissolve, another charged thing. So water dissolves anything that's got charges on it. But it doesn't really dissolve very well with oil. Oil and water don't mix. Why? Because oil is mostly polar bonds. Okay? All right. They're, of course, if they're alkanes and not alkenes, they're saturated. We talked about what saturated meant last chapter a little bit. Mentioned it again here. What does it mean to be saturated? What is the word? What do you think of when you think of saturated? Think of saturated fats. Okay, well, some people, by the way, in your essay question answers yesterday about trans fat, called them saturated fats. They are not saturated fats. They are by no means saturated. What does saturated mean? Yeah, they're filled with hydrogens. As many hydrogens as you can have. Remember, I drew it like this. If I draw let's just take a simple carbon compound like propane. Don't draw this, you don't have to. I have as many hydrogens as I can have around here. In this case, I have 1, 2, 3, 4, 5, 6, 7, 8. But if I have any unsaturation in them, I now no longer have the maximum number of carbons around him. So that's why we call him unsaturated. And to get back to your answer, everybody was here for the test yesterday, right? Nobody missed it? Back to your answer for that. Hydrogenation, what it does is it takes saturated fats, all right, and it breaks them, and it makes double bonds in them. All right, and that's not what makes, according to the article I gave you, what makes them healthy. It puts double bonds in there, and what happens is you get trans and cis. You get trans fatty acids as well. In nature, generally, for the most part, there are very few exceptions, but there are a few. For the most part, in nature, most of your fats are going to be cis. Most of the double bonds are going to be cis. All right, so you get a lot more trans fats when you do that. Now, whether or not that's going to kill you tomorrow, I don't think so, but they banned them in many places, and of course, all the products have their labels on them. No trans fats. All right, this one is also pretty obvious. If you think about the, as you go up the scale for larger and larger alkanes, the boiling point's going to rise about 30 degrees approximately with each additional carbon that you add to it. I have been looking up some AP questions in different places, and I ran across a question that gave you two compounds and asked you about boiling points. Which one would have a higher boiling point? Well, one way you can tell right off the bat is as they get bigger. Look, here's methane. Okay. Methane, ethane, propane, butane. And by the way, let's think about some of these things. You don't have to write these down, obviously. They're not on your thing. Let's think about some of these things. Methane and ethane are both pretty much components of natural gas. All right, so that's, natural gas. The stuff that comes out of the pipes right there. I'm going to use that in a little bit for a demo. We know what propane is. What's propane? That's in your gas grills, right? It's your barbecue grill. That's in a gas grill. Is it also a gas? Sure. Now, butane is in this lighter here. And I can shake it up and even hear it in there. Okay? It's under a little bit of pressure to keep it a liquid. So it's kind of, depending on the pressure, depending on the temperature, it's almost a liquid, but it's in lighters. Like cigarette lighters. Heck, let's go all the way down to octane. What do we think of? What have you heard the word octane around? Yeah, it's even in your gas tanks. You're going to use octane in cars. So we know that's a liquid. Okay, that's basically gasoline. Although it's not really octane, it's actually a lot more branching in it, so it doesn't knock as much. So look we've got a very light gas like methane. And by the way, one of the things I'm going to do back there, I'm able to say it here while I'm here because I'm going to turn the camera off when I go back and do that. In the old days, I used to have, before they hooked us up in the school, the whole school got hooked up to the city gas, the natural gas line. All right? And so these jets right here, these jets used to have a big tank out here, a huge propane tank. We used to have propane, and now we have methane. And I used to do this demo back then. And what I would have to do is I'd have to get a chair, back in the days, climb up on that chair, and I would make a bubble of propane gas. I had to get up on a chair and do it at the ceiling because once that bubble was made, a propane gas was a soap bubble, it would fall down because propane is heavier than air. Now, first time I did this, first year we got this, I forgot they changed the lines. And I went and did it, standing up in my thing, and I made my gas bubble, and where'd it go? Went to the ceiling. Because methane is lighter than air. And that's why from now on I got to do it down here, and the bubble rises. It's actually harder because I want somebody has to help me and light this bubble on fire. All right, whoever I choose to. Hair burn. Don't worry, you won't. I've got a long stick, and you'll wear glasses. All right, so, but my point is, very light gas, methane. Propane's a heavier gas, but still a gas. Butane's almost a liquid, and octane is a liquid. And if you look at the temperatures, the boiling point of methane, negative 161. It doesn't turn into a liquid until negative 161 degrees Celsius. As they get up, look at higher and higher and higher. When we get to butane, like I said, butane, depending on the pressure, I could even turn him into a liquid. Anything above 0 and a little bit of pressure. Octane is already a liquid. It doesn't boil until 125 degrees Celsius. Okay? All right. So your boiling point rises the bigger the carbon. And that makes sense, by the way. Let's think about this. Why does that make sense? And I'm trying to relate some of this stuff to things you'll see on the AP exam. The reason that makes sense is the larger the molecules, the greater the intermolecular forces. I'll have to review this with you when we get to, before the AP exam. But intermolecular forces like dipole-dipole attractions and hydrogen bonding and London dispersion forces. Those kind of forces, well, in a nonpolar molecule, you don't have those. You only have the London dispersion forces. You only have the weakest ones, the weakest van der Waals forces. And the more of them you have, the larger the atoms are and the larger the molecules, the stronger that force. And that's why they get heavier and heavier and harder and harder to boil. They're held together a little bit tighter. Okay? The intermolecular forces holding them together a little bit tighter. All right. Oops. All right. So, there's one other thing that happens with boiling point. Okay? It decreases with branching. So if I were to give you a compound, and I'm going to do this in this test, guaranteed. Like I said, I actually saw in preparation, reading over some AP exam questions, I actually saw a question like this. So say, for example, I gave you a compound, all things being equal. In other words, this guy's got 1, 2, 3, 4, 5, 6, 7, 8. It's octane. All right, and this also has 1, 2, 3, 4, 5, 6, 7, 8. Also has 8 carbons. You might think, well, based on this first rule, they're going to be about the same boiling point. But based on this rule, all right, what do we know? This guy's going to have a lower boiling point because he's got more branches coming out. This being a branch being carbon chain, however long, coming off of a longer chain. So this guy's going to have a lower boiling point. And by the way, guess what I'm going to give you over the course of the next couple of weeks? You could also add OH groups on there, or carboxylic acid groups on there. Okay? And when we do that, that also will affect the boiling point. All right? And we'll have to talk about how that will affect it. So I will give you a compound with these different possibilities and ask you who would boil higher, who would boil lower. All right? Now, forgetting about these guys here, okay, if I have just a straight chain, and then I've got the same number of carbons, but in branches, that guy's going to boil at a lower temperature than this guy. If I have this guy versus this guy, who boils at the lower temperature now? This guy versus this guy, both in a straight chain. What do you think? Who's going to boil at the lower temperature? Butane, right? Versus octane, because he doesn't have as many carbons. All right, simple as that. All right, so that's one kind of question you could get on this. By the way, this test is going to be another one of those tests where I'm going to take 2 days to do it, unless we have a double period when I work it out. I will try to work it out on a double period, because there's no way you can finish this one, because there's going to be a separate test, and this is a good thing for you. You don't have to be thinking about everything at once. There'll be a separate test for about the properties of each of the guys we're going to talk about. So that's going to be a memorization test. Then there'll be another test that's all about the reactions. Okay, we'll talk about those. All right, let's get to going. All right, so those are the properties of alkanes that you really need to know. Let's start talking about the reactions. Like I said, the number one, the biggie, is combustion. All right, that's the guy that's most important. It happens to also be the least likely. I mean, it's not really that difficult, and least likely I'm going to give you a whole lot to do with this. Alkanes will be involved in many other reactions, synthesis reactions of other things, but not using the combustion reaction. Because in the combustion reaction, what you do with an alkane is you basically rip it apart and turn them into carbon dioxide and water, as you know. You're combining it with oxygen or burning it. however long that alkane was, you're going to end up with two products. And what are they? Look at the reaction. Look at the general formula below.
Carbon dioxide.
Yeah, you're going to end up with carbon dioxide and water. All right? And by the way, there's a few things to get used to seeing when we start doing these. I didn't have to put it this way, but I did. When you see an R group, that means some alkyl group of some type, some alkane or some alkyl group of some length. That R can be 1 carbon long with the correct number of H's around them, or he can be 100 carbons long. All right? And generally, the reason I have RH and not just an R, all right, because you're going to see a lot of different things attached to that R. Over the course of the next month, you're going to see R, maybe Cl, which I'll call Rx. So any halogen attached to it is going to be, and you're going to see one of those just in a little bit. You can have ROH. You know what we'll call those? You should know because we're making it right over there. What are those called? Any alkane attached to an OH? An alcohol. You're making alcohol right over there. You can have R-C-O-O-OH, that's a carboxylic acid. R-C-O-O-R, that's a ketone. There's esters, there's aldehydes, there's amines, ethers. All these guys are going to talk about. And R always means some number of carbons and then attached to something else. Some alkyl group attached to something else. Okay? So, if I take my alkane, in this case it's just an H that it's attached to. So my alkyl group would be however long, and an H means it's just going to be an alkane. I burn him with oxygen, and I get the same two things. Let's try 2 examples of this. I think I have room for 2 examples, don't I? Okay. Let's try 2 examples of this. I don't know if I have it written down here or not. Example 1, no, okay. So I'll do it myself here. All right. For the first one, we'll just take the easiest guy you can take. CH4 plus O2. Now, let me stop you right there. And everybody look up here. I told you there are 2 tests. On the test, that's going to be reactions. One, I could show it to you. I'm going to show it to you right now. I can't show it to you on the camera, but I'll show it to you right now. Here's the test. All it is the left side of the equation, and then you finish it. Do you remember a test like that in Chem 1? There was. The test like that in Chem 1 where I had just composition, decomposition, replacement, and exchange reactions. And I had all the left sides, and you just had to finish it. That's exactly what you will do here. What makes these a little bit harder is that, well, I don't know if it's harder, but certainly the brand new system. You know, when you did the inorganic stuff, I mean, you were taking stuff like NaCl plus whatever, right? So I told you had to name everybody. Sodium, chloride. That was pretty easy to name those, right? Well, these guys, you're going to have to name the same way we had to name them before. You know, 2,2-dimethyl, 3-ethyl, 4, whatever. The same stuff you had to do for the last chapter, you're going to use to name each of these guys underneath him. Okay? Let me get rid of that. And this is a pretty simple equation. What is it always going to give me as my product? 2 things. The CO2 and the water. And of course, just like you had to do in those in Chem 1, you have to balance them. How do I balance this guy? Can you do it? See if you can figure out how to balance that guy. Not hard. Pretty simple, isn't it? Who got it balanced? What'd you get?
You put a 2 in front of the O2 and a 2 in front of the H2O.
Exactly, because you have 4 H's, so you put a 2 there. That gives you 4 H's there. Now you've got 2 and 2 is 4 O's, so I'll put a 2 in there. 2 times 2 is 4 O's. That is nice, but watch this next one. So why did I do 2 examples? This is pretty easy. Here's why I did a second example. Try this guy. I'll just make him 1 guy bigger, and you'll see what happens. Oh, and by the way, you should also name, you would have to also name this guy underneath him. What was his name? Methane. Yeah. And what's the name of this guy? Ethane. All right. Now, when you go and do this guy, There's no difference in the products. You're still getting the same two guys, CO2 plus H2O. All right? And when you burn things, generally the water is in the form of a gas too, steam, right? And CO2 is a gas. So when you burn this, you basically get gases that come out your tailpipe if you're burning octane, if you're burning your gasoline. Or if I'm burning this, you know, what is that? What am I burning in here? What did I say is in here? Butane. Okay. All right. Balance that guy. Not quite so easy, but you can do it. You'll see what happens. I think most of you are probably running into it right now. You try to balance this guy. You see you got 6 hydrogens here, so let's just try doing it the way I'm sure you're doing it at first. You said, okay, I got 6 H's there, I'll put a 3 there. 3 times 2 is 6 H's. Great. I've got 2 O's here and 3 O's there is 5 O's, right? Oh boy, what do I got to do here? I can't multiply anything by 2 to give me a 5, can I? Let's try it. I want you to think, because sometimes you have to think like this. What would it take? What fraction would it take to multiply this guy to give me a 5? 5 halves, right? 5 halves, right? Okay, is it balanced now? Technically it's balanced, isn't it? Or is it? Oh, yeah, we need 2 carbons. Right, sorry, we need 2 carbons. And then it wouldn't be 5 halves. My fault. That was dumb. I should have done that one first. All right, but I am going somewhere with this. Trust me. All right, so what would I need in front of that guy again? 7. Now it'd be 7, right? Because I have 2 times 2 is 4, and 5, 6, 7. 7 halves. The problem that made this guy a problem was the odd number of O's over there, right? That was what made it a problem. I forgot about the carbon. All right, now, what can I do? It's balanced now. Technically it's balanced, but I know I can't have a half an oxygen molecule. So what can I do to everybody that will balance the whole equation and not have any fractions in it? Exactly, just multiply everybody by 2. So basically you end up with 2C2H6 plus 7O2 yields 4CO2 plus 6H2O. Got it? Okay. And that happens sometimes. You got to do that. I got a little bonus thing for you. All right, if by tomorrow, whoever wants to get, I'll give it to anybody who gets it. So if you get it, you shouldn't share it. And can you come up with, and if you could do this forever, like I could have C3, C4, C5, all the alkanes I could do. But there is a way in terms of N, CnH. What is the formula for an alkane? 2N plus 2. There is, believe it or not, a way to actually solve in terms of N for any equation. In other words, where you could have the O2. They're always going to be these guys here. Okay? You can put this on the back if you want to try this. In terms of N, in front of each of these guys, and in front of this guy. Okay? In terms of N. Now let's just make something up. It's not going to be right. So in other words, it could be 3N, 2N, or 1/2 N, or 2N plus 2. In terms of N, can you balance any equation, you know, with a generic algebraic formula? It is possible. All right? Okay? And if you can figure that out, that would be nice. I'll give you a bonus point. Okay? So what I'm saying is, when you're all done, your equation should look something like this. Cn H2n plus 2 plus something in terms of n, like 3n or 2/2 n or whatever, plus 3n plus 4n in terms of n, not in terms of actual numbers. Okay? See if you can figure that out. I will give it to you in the future if you don't get it, but you don't need it. You don't really need it. The fact is, you can. None of these are that hard to balance, but it is kind of neat to just think algebraically sometimes. All right, so that's combustion. I will on the test give you half the equation. You got to finish it and name everybody in it. Let's do the next guy, halogenation. Oh, by the way, that combustion one, I'm going to do a demo after I shut the camera off. There's my demo for the camera. I'm burning butane. Okay, if I were to have done the next one or 2 more up here, C4H10, that would be butane. But I'm going to do one back there because it's kind of cool, if we have time and if I get it to work. But in the meantime, let's do the other two reactions. Halogenation. Halogenation is a substitution reaction. Now, what you find when you start classifying, these reactions as different types, they fit into a pattern. So that you're not the reason we do this, you don't want to end up having to memorize individually, literally, hundreds of different kinds of reactions by the time we're done. I mean, actually, we're not going to get hundreds. We're going to get about 25 or 26 different reactions by the time we're done. Well, a lot of them are very similar, all right? Substitution reactions are very common. And matter of fact, when I go to talk about mechanisms, I'm going to talk about substitution reactions, and there are a lot of guys that we're going to talk about over the course of the next month are going to fit into this. Because what happens in a substitution is exactly what it sounds like. One atom is substituted for another one, okay? Here's what the general reaction looks like. See if you can figure this out. You have this already. By the way, that's why all of these are filled in for you too. Saves me a little bit of time, makes it easier for me to teach it. What's happening here? What do you think X probably stands for in this case? What do you think? Nope, not an oxygen. A halogen, because it's halogenation. Right. And why? Here's another clue. Here's another clue as you could tell it was a halogen. What does he have next to him? Yeah, all the halogens we know of are diatomic, aren't they? Okay. So look what happens. Can you see it? What's happening here? The H is kicked out by an X. He gets together with the other X and makes HX, right? And that X goes on there. Pretty easy, huh? All right, that's exactly what's happening in a substitution reaction. Pretty cool. All right. Oh, and by the way, these little guys down there, I think they're underneath yours, they mean heat and light. We're going to talk about the mechanism for this reaction, by the way. It's one of the first ones we're going to do, halogenation. And we're going to talk about what the heat and light do there and some other stuff. All right, let's do some examples. I only have one example of this guy. Let's do one example of this guy. I do have room for an example, don't I, there?
Yeah.
Okay. All right. Now, here's a good place where I can... Well, no, I'll just take an easy one. Okay? Finish that. See if you can finish that on your own. You need, when I say finish it, you know what I mean. You've got to complete the equation, balance the equation, and name everybody. Now, by the way, I say name everybody. You do not need to name non-organic stuff. Don't need to name chlorine. Don't need to name chlorine. And you don't need to name the HX that's going to be formed on the air side either. Just the organic stuff. I hope you all know how to name everything. Now, even though I don't have them drawn in there, we know at the end of every one of these dashes it's an H, right? So, what's happening here is you're going to get this. I hope. That's how you have to draw it. Exactly how you have to draw it. I have people who always will put X's in there anymore. No, I'm specific now. The X stands for any halogen. The chlorine is the specific halogen I'm using in this problem, so I have to draw it like that. Now, when I say I have to draw it like that, could the Cl have been here or here or here or here or here? Sure.
Oh, wait, that's not right.
What did you mean?
I meant like, okay, so normally we would write C2H6, right? For the other one, do we have to draw it or do we have to...
You have to draw out the structural formula. The only one you don't do that with is the combustion ones, because in that case, you really don't have on the other side a structural formula. You just have carbon dioxide and water anyway. But on these guys, I'm going to have you draw the structural formulas like you were doing all last chapter. And it makes it easier to name it. What's the name of this guy? Ethane. I don't have to name chlorine. I know chlorine. I hope you all know chlorine. This guy would be what? Chloroethane or 1-chloroethane. I don't really care. If you put the 1 in front of it, it's not wrong. It's just not needed. right? Because there's only one place. Now, if I had used propane, and I had the chlorine on, I have to put 2 chloro versus 1 chloro. And by the way, you're going to learn later on, and I want you to realize this, that in general, these guys, we haven't talked about the mechanism yet, we won't until next unit. The guys that you're adding on, as you'll see when we go on, are generally going to go more towards the center of the chain. I purposely chose a guy that has only, there's no difference. If I put the chlorine here, if I put them here, it's the same exact compound. But if I were to have given you a guy like propane, you know where that chlorine would have probably wanted to have gone? Most of the time, where would it have gone? Into the middle one, okay? It would have gone there. All right, and we'll learn why when we get to the mechanisms. It has to do with a lot of other stuff. Actually, you'll learn why even a little bit in this chapter when we talk about double bonds. And it's not 100%. You don't get 100% added onto that guy. But that will be the more dominant product. Okay. And cracking is the last one we have to talk about here before I start my little demo. All right, cracking is not what happens when the refrigerator repairman bends over to repair your refrigerator. It's also not what happens when you're making crack for people.
Oh.
That would be another way.
Didn't see that one.
Didn't see that one. Cracking is a very non-specific reaction. You basically heat the stuff up without any oxygen around. Because if I heat it up with oxygen around, it's going to burn, right? If I get it above a certain temperature, if I get a spark around, it's going to burn. But if I heat them up without oxygen around, with a catalyst, and I'm going to get cracking. That's kind of what happens in your when you're making what's the word? Those trans fats we were talking about. Remember those trans? All right. You're heating it with a catalyst, but in a sense, you're actually adding a hydrogenation of existing double bonds you already had. All right. Sometimes they will add across and give you trans instead of cis. All right. But if I crack an alkane, I will get 2 things. I'll get exactly what it says. It cracked into a shorter chain. But I'll also get a double bond when that happens. Okay, so watch this. Look at the general formula. The alkane is going to yield another alkane, a shorter alkane, plus an alkene. So let me show you an example. Okay, let's just say a guy like this one. It should be a little. Is there a triangle under yours, I think?
Yeah.
Okay. All right. That means a triangle means heat, not just change like it does in math class. Now, is there only one answer to this? No. There are probably 4 or 5 answers for this. Okay? Watch. I'll draw one answer. The alkane I could get could be this alkane. And the alkene I could get could be this alkene. Okay? Could I also have drawn just a methane and a butene here? Or a propane and an ethene here? Absolutely. This is a very non-specific reaction. You can't get just one, you don't ever get just one product from this. Name everybody on there, though. Go ahead. Because you do have to name everybody below him. And then that's the last thing we're doing. Name them. Go ahead. And you might say, don't I need a 1 in front of the propene? And it wouldn't hurt. It wouldn't be wrong. But in the case of propene, whichever one it's on, it's still 1. Okay? Lowest number possible. And there you have it. Okay? What would I give you on the test? I could give you any of these guys with a specific example. So instead of giving you pentane, I could have given you just butane. Or I could have given you a very long one, like 2-methyl, 3-ethyl, whatever. And you would have to have done this big, long guy. And you could crack him anywhere you want to. I don't care, as long as you do it correctly, as long as it all adds up on the other side. All right? Okay.